Good evening, everyone. So please let me know if I'm audible, and then we can start the today's session. So am I audible? So please let me know. Okay. Okay. So let us now start in today's session with one more important topic, and this from production engineering, and this is called as rolling, right? As you know, in case of metal forming processes, you're having many different topics, like you're having rolling, you're having this wire drawing, forging, extrusion, etc., right? And deep drawing, etc. All those topics are there. So one of the important topic, rolling, even though it's pretty simple topic, right? Normally in the normal class it may take 5 to 6 hours, but in the form of a like crash course you can cover it within 2 hours or so. Within this time you must be able to understand and must be able to solve all the related problems, because problems are not that difficult, and if you have some basic understanding, then I think any problem related to this topic can be solved, and the question is also frequently framed from this particular topic. So that is why we have selected this topic under the most important topics list that is provided to you. Okay. So I will not go into detail of basic of rolling process and all that, but I will just give you one brief idea that how is the rolling machine and all that. So basically, as you know, this is a continuous casting, from where after getting this continuous casting we have the different products of different shapes, and normally these are the larger products normally that we get after the molten state. That means after continuous casting you solidify the metal, that these are the major products that you obtain. And the topic that we are going to discuss is basically the rolling of the sheets. It means the product that I am going to have, it should have relatively higher width, and then I'm going to deform it to a thickness of relatively I need to deform it to a relatively smaller thickness. So for that I need to have a product initial raw material in the form of slab. So if you can just have a look, it is having a significant width and obviously length also. Then I will deform this length or this slab into smaller thickness, and that process of reducing the thickness of the slab, or maybe then you're a sheet, we call it as a rolling process, and that to a rolling of the flat sheets, right? Because I'm having a flat product. You're having other products also, but they are used for like wire drawing, other purposes, for example, all that. So that we will see the reference in case of wire drawing and other areas. So I don't need to discuss all these things, but something like this you can visualize. You're having these sheets. For example, these are hot rolled coil. This is deformed to cold rolled coil. So it is having a higher thickness. So I want to reduce into the some smaller thickness, something that way, right? So then I would like to show you the process. Basically I want you to show the process. This is something like the flat rolling process is. This is the actual machine that you can see. So this is the cold rolling machine. Okay. So I will give you a very brief overview so that when you are attempting the question you should not have any confusion. So this is a kind of roll. It's like a paper roll, right? Only difference being here it is a roll of sheet or of metal sheet, right? So this thickness I have to reduce. So what I need to do is I have to pass it through the rollers, and something this way. Just a minute. Something this way, okay? So here you're having the two rollers. So what I will do, these rollers I will be supplying the power with the help of motor over here also. So obviously what will happen is that when you rotate this way, so you're having a sheet of larger thickness. It doesn't seems like sheet, but anyway you can just imagine it like a sheet of higher thickness, let us say H1. So by passing it through between these two rolls are basically going to squeeze this sheet. So when these two rollers are going to squeeze, then obviously you are reducing this thickness from a certain value H1 to final thickness of, let us say, H2. So this process of reducing the thickness of initial raw sheet of higher thickness to a smaller thickness, we called it as a rolling of the flat sheets, right? Now in the form of, obviously since this is a sheet, it is going to have a certain width also, right? Now same process, this process of like converting it is done in the machine called as rolling machine, right? So this is the rolling machine. These are the rollers between which you are going to squeeze. These are the rollers. These are the rollers. Okay, this is a set of the rollers, for example, between which you are going to pass it and then going to deform. So these rollers are fixed on the machine. So over here you are going to have this machine. So just have a look briefly on this particular machine. So this is a rolling machine. Okay, more specifically, this is a cold rolling operation. So this is a cold rolling machine. So on one end, you are going to fix this particular sheet, this particular roll of the sheet, and going to pass it over here. You're going to have, okay, let me choose the color that you're going to have over here. Okay. So what you're going to have, you're having the rollers over here. So you're going to pass it through this. And obviously over there also, you're going to round it again. This way, winding will take place. So from one end, you're going to other end. And then because it is not only in one stage. Now the term that you need to remember over here is the passes. Passes mean how many times you are passing this sheet from one end to the other end. For example, when you are uncoiling from this end, when the sheet is going from this side to the other end, then obviously certain deformation is going to take place. And to save the time, what we normally do is we can reverse the direction of these rolls. So first this will go from here to here, certain amount of thickness reduction will take place. And then, so initially, let us say you're having this gap, okay? This is the gap that you're having. So you reduce the thickness this way. The other end, you are having the coil. Now what we will do? So in this case, you're going to have the direction of rotation this way if you're moving from this side. Am I correct? Only then you can squeeze it. Now, because you want to save the time, so what you have done is you can reverse the direction of these rollers. Right. So let us say now I have a reduced thickness sheet over here. So I want to reduce it further. So what I will do, I will now again allow it to pass to the same set of the rollers, but in this direction. So what I will do, I will reduce the gap between these rollers and I will pass it again in this direction. So I will just do the same thing to this now. Okay. What I'm doing is I'm having these rollers again, but the gap that I'm having between these rollers, I'm going to reduce that gap. Okay, something this way. Now you can see. Now same sheet which was over on this side. Now what I will do, I will change the direction of this particular rollers and reduce the gap between these rollers. So again, I'm going to have a reduced thickness sheet on this side. So when I pass this sheet from this side to this side, I call it as a one pass, one stage or one pass. Now I'm reversing the direction. Then again, you are further reducing the thickness. When you're going from this side to this side, then I will say this is the second pass. So you cannot reduce a sheet of higher thickness into the final thickness, desired thickness in one stage only, in one pass only. It is not possible for us to reduce the thickness. Let us say you want to reduce the thickness from 6 mm from this side to 2 mm. So it is not possible for us to reduce this 6 mm to 2 mm in one step only. So what I need to do? I have to first pass it, reduce the thickness, smaller thickness. First I reduce to 6 to 4. Let us say first I reduce from 6 to, that 2 is too large, 6 to 5 mm. Then I reverse the direction. Then I'm passing it through the second pass. Then now sheet is being passed this way. So 5 to then again, let us say 4 mm. Then this 4 mm further reverse the direction. Another pass 3 mm. So that way, by reversing the direction and reducing the gap, subsequently I can reduce that thickness, higher thickness into smaller thickness in number of stages or number of passes. So that is the point that you have to keep it in mind. What is the meaning of pass? Pass is simply when you pass that sheet from one side to another. So during that some reduction will take place. But since I want further reduction, so again I have to give one more pass. So that way we can carry out this operation. So this is the actual operation that you can have. But this term will going to appear over there when we are going to discuss the numericals with you. What is the meaning of pass? This is just the front view from this side. If you are looking at it, that much information you need to have. Okay, rest. These are the rollers, actual rollers basically, which you are going to place it over here. You can take them out, you can fix them up. You can just see over there. You're going to have bearings and all those arrangement that is you're going to have. So I think that is all that much information or basic information you need to have. Now, once that is done, then I think we can move on to the mechanism of the rolling process, which is important for us from the exam point of view, or the numerical aspects that we need to discuss with you. Okay, so it's the same process that I discussed with you. I have shown you earlier also, but some dimensions have been provided. These dimensions we are going to use on this particular as we move on in the further discussion. So just have a look. So just keep it in mind, the direction of rotation of these rollers should be opposite. For example, if this is rotating clockwise, this has to rotate in anti-clockwise direction only then, because basically I want to move this sheet from one end to another. So how I can move? When I will rotate this way. So when I will rotate these rollers this way and squeeze them, then obviously this rotation is clockwise, whereas this rotation is anti-clockwise. Only then I can move this sheet from one end to the another. So let us say you're having a initial thickness of the sheet, which I am going to denote with H1, and it is going to have a certain width, let us say B1, and the other end, after this material or this sheet gets deformed, so I am reducing this to a thickness, let us say H2, and the final width that you're going to have will be B2. Okay, in rolling process, most of the deformation is going to take place along the length, because you are reducing the thickness. So by reducing the thickness, mainly the length is going to increase. The change in width is going to be insignificant or very small. So we will see it that if you are having B1, more or less it is going to be equal to B1 only. So width change is not going to be that much. That information you must have. Okay. So this is the basic description of the flat rolling. Now I need to explain you some of the terms, then I think we can discuss the, okay, this is the mechanism of that, we call it as a flat rolling. Okay, so let me just write these words that way, mechanism of flat rolling. So now just have a look, same figure has been given to you, only in two-dimensional. This is the two-dimensional figure. Now see the terms that I'm going to use over here. They are going to be the, if you know those terms, then it will become pretty easy, simple for us. Okay. Now these are the two rollers. Now see, this is the portion of the rolls. This is the portion of the rolls which is coming in contact with the strip. So now I can call it as a strip. I can call it as a sheet, whatever you want to call it. So when you are deforming from this, like you are passing the sheet from this end to the other end, let us say in one pass. So this is the area, or this is the length of the, or the portion of the sheet which is coming in contact with the rolls. Okay. So we can call this as a contact length. So if I say this is also AB, you can say. So here the term going to appear over here is going to be the AB. AB is going to be the roll strip contact length, whatever you call it, roll strip contact length or simply contact length, right? So you can call it as a roll strip, that is the contact between the roll and the strip, roll strip contact length, or simply you can say, most of the time we simply say contact length, that is understood, contact length. Clear? So, and let us say this is the initial thickness H1. I'm deforming it to the final thickness H2, and I'm not showing you the width, but let us say width is B1, and final width, as I am saying, is going to be B2, but it is more or less equal to B1. Now let us say this strip at the initial, at the inlet end is moving with a velocity, let us say V1, and obviously since you are deforming it, cross-sectional area changes, we will say that volume flow rate is going to remain same. So obviously we are left out with no option but the velocity. You are going to have a different velocity at the other end. That we will see with the help of that volume flow rate equation. That comparison we will carry out. But as of now, just keep it in mind. Let us say this is the initial velocity of the strip. I'm talking about the strip or the sheet. Then let us say at the final velocity you are going to have, let us say, is V2 at the end. Okay, and this is a roll, and this is the center of these rolls. I'm just discussing for this roll. It is going to have the same situation for over here also. So these are the radius of the rolls. Let us say, if you see over here, I have defined one angle called as alpha, right? And this angle basically is the angle subtended by this particular arc of contact. You can call it as an arc of contact also, right? Or arc of contact, meaning is same. So this is the angle that is subtended by this contact length or arc of contact, or the roll stripped contact length at the center of the rolls. So this angle is called as contact angle. or you can also say alternate name is angle of bite. तो angle of bite, bite क्या होती है? जब आप खाना खाते हो तो you bite something. Some same way, basically this portion is biting the strip. That is from where that name has come. So you can say this is the alpha is the angle subtended by this. Also, angle of bite is the angle subtended by the roll strip contact length at the center of the roll. Okay. In addition to it, I have shown one red line over here. If you can just have a look over here. This initial plane, this if you see, if you draw a plane from the points where the initial contact takes place, this is the portion where initial contact of the strip. Initially, strip was coming in contact over here. This was the situation, and gradually, as it was pulled by these rollers, gradually as it was pulled by these rotating rollers, so this cross section was reduced. So can I say this is the what? This is the inlet plane. Same way, the points where this strip is coming out after deforming, I have denoted this BB, you can say. So at here, you're going to have a plane. If I pass a plane over there, passing through these 2 points over here, I will call it as a exit plane. Okay. And somewhere in between, we don't know exactly where is the location. There's going to be one more plane called as the neutral plane. So this red line, dotted line that I have shown you, we call it as a neutral plane. So what is the meaning of neutral plane that I will discuss with you? But this is how the situation. This is the neutral plane. Okay. Now, see, rolls will be rotating with a constant angular velocity because you're rotating, you are supplying the power with the help of a motor. You're having one motor over here which is rotating this roller. You're having one motor over here which is rotating this roller. So both of these rollers are rotating with the same angular velocity. So let us say if I say it is rotating with an angular velocity of omega, then if I ask you what is the tangential velocity on the periphery of this roller, so you will simply say at any point on the surface of this roller, of these rollers, the tangential velocity that is going to be what? V is equal to omega into r. And over here I have denoted this r as the radius of the roller, and since the radius of the roller, both the rollers is the same, so obviously at any point on the surface of these rollers you're going to have the same tangential velocity, or I can call this as velocity as the roller velocity also, tangential velocity of the rollers also. It is up to you. So just keep in mind that this velocity of the rollers, tangential velocity or angular velocity of these rollers is going to be constant. Now think of a situation initially when you are having that strip coming in contact with the rollers. Over here, this strip came into contact with the rollers at the inlet plane, right? So when the strip came into contact with the rollers, let us say I was just passing it through this particular, let us say with V1 velocity. Now, because these are rotating with a certain angular velocity omega 1, definitely this is going to be higher than this. This velocity, initial velocity, maybe simply you are just bringing that sheet in contact with the rollers. So that very small velocity, you can say, is the initial velocity. Whereas from the very beginning, these rollers are rotating with angular velocity. So this angular velocity or surface velocity of these rollers at any particular point is going to be quite higher than that particular initial velocity. So it means when this strip came in contact with the rollers over here, the strip velocity compared to the roller's tangential velocity, what will be the tangential velocity of the rollers? You can say this way. Same way over here, tangential velocity of the roller is going to be this way, right? So that velocity is going to be significantly higher than the what? Sorry, roller velocity is going to be significantly, tangential velocity of roller is going to be significantly higher than the velocity of the strip. Now, as the deformation continues, now there will be change in the velocity of the strip. And as you know, whatever the flow rate of that material that is from the inlet towards the exit, as the material is moving forward, if you want that continue to be maintained or you want the homogeneous deformation of this material, then at any particular section, the volume flow rate of this material should be same. It should not happen that volume flow rate at this section and at this section is different. In that case, that deformation is going to be inhomogeneous, and therefore the sheet that is coming out may not be proper. So if you want that sheet that is coming out is having uniform thickness, uniform kind of properties, then obviously at any section that you are considering, the volume flow rate should remain constant. So if you apply the volume flow rate equation at any particular sections between the inlet and the exit, then I think you can get some kind of result. So let us say what I'm doing is, let us say I'm applying the volume flow rate equation between the inlet and exit. You can apply between any two sections. So just for the sake of explanation, I'm taking between inlet and outlet. So can you let me know, if I apply the volume flow rate means you are representing that volume of the material with respect to time, either mm³ per second or maybe meter cube per second, meter cube per minute, all that, right? So now if I take that way, then how do you write the volume flow rate? Can I write this way? A1, that is at the initial section, let us say over here, A1 cross section area over here into V1 is the velocity at the inlet over here, should be equal to what? Cross sectional area at BB, that is, can I say it is A2? So cross sectional area at A2 and velocity at exit, which is V2, I have denoted. Basically, whenever this material is come out from this point onwards, you're going to have the velocity V2, which I have represented already over there, right? Okay. So now, how can you represent the cross sectional area? At the inlet, you know the thickness and width is perpendicular to this board. So can I write this? This H1 B1 V1, H1 V1 thickness, width, that becomes the cross sectional area. V1 initial velocity, H2 B2 V2. So as I told you that roughly, because the way the deformation is taking place, majorly the length is going to increase. There is very slight or almost negligible change in the width. So if that be the case, then I can say that this width almost V1 is going to be equal to V2. Then can I say that what is the velocity V2 will be? So can I say H1 by H2 into V1? Now tell me, since you're having H1 greater than H2, am I correct? Am I correct? H1 is greater than H2. Obviously, this thickness is greater than H2. Then obviously, if H1 is greater than H2, this total value is going to be more than 1. Then obviously, V2 is going to be greater than V1. So there, since this is there, so V2 is going to be greater than V1. That's the meaning of. So what is the meaning of this? If you want to maintain the volume flow consistency, in that case, the velocity of the strip should continuously increase. It means the velocity of the strip must have increased from initial value of V1 to a final velocity of V2. And that is going to be the situation anywhere at any particular two sections that we are going to take. So as we are moving from inlet towards the outlet, the volume flow rate equation should be satisfied. In that case, velocity should be increasing continuously towards the exit. So keep it in mind, you may have to utilize this volume flow consistency equation in the numericals directly as it is. Okay, so just pay attention to that. So you don't need to like something special knowledge for this. Simply you have that understanding. Same way, one more section I can take for the sake of explanation. Let us say I defined one more section over there called as neutral plane. Now tell me, I told you neutral plane is somewhere in between, right? So why I defined the neutral plane, or what is the meaning of neutral plane? Now I can let you know. Now, as you know, the velocity initially, as I told you, initially the strip velocity was far lesser than the roll velocity, roll tangential velocity. But as the strip moved inside this roll gap, then strip velocity continuously went on increasing. As strip velocity continuously went on increasing, there is going to be one point over here, somewhere in between, where the strip velocity will become equal to the roll velocity, tangential velocity of the roll over here. Okay, so it means the points where, or the section or the plane where the strip velocity, which is continuously increasing from inlet to outlet, becomes equal to the roll tangential velocity of the rolls. that plane is called as neutral plane, that I have denoted over here. Obviously, after the neutral plane, say, see, this is the point. So as you are going toward this side, so velocity was continuously increasing. At these points, the velocity matches with the tangential velocity of the roll over here. And as you move further, since roller velocity is remaining constant, only velocity that will be increasing will be of strip, because cross-sectional area of the strip is further decreasing. It means strip velocity will continue to increase till the exit. It means after the neutral point, the strip velocity will become more than the roll velocity and go on increasing. Then finally, obviously, going to have the V2. Right? So this is the situation that you are going to have over here. So let me sum it up what I said. To satisfy the volume flow requirement, right, what is going to happen is when the strip moves inside the roll gaps, then strip velocity will continuously increase from inlet to outlet, whereas the tangential velocity of the rollers, that is going to remain constant. So initially strip velocity was far less than the tangential velocity of the rollers. As it moved further inside the roll gap, the strip velocity went on increasing, and there was one point was reached somewhere in between where strip velocity became equal to the roller velocity, which is constant. Roller velocity is constant. Now, even since the area is getting reduced further, so strip velocity will continue to increase towards the exit, whereas roll velocity is going to remain same. So after the neutral point, strip velocity will be higher than the roll velocity, and before the neutral point, strip velocity will be lower than the roll velocity, tangential velocity of the roller. So that is the point that you have to keep it in mind. So if that you have in mind, so anywhere between any two sections you can apply the volume consistency equation. So what I'm doing is I can take inlet or neutral or outlet. So let us say I'm taking inlet and neutral. So can I say this way? So A1 V1 inlet should be equal to AN, cross-sectional area at neutral plane, into velocity at neutral plane, isn't it? So what is the area that is over here? H1 B1 V1 is equal to what is the cross-sectional area at the neutral plane. So for that I need to know the thickness over here. So let us say I am saying the thickness at the neutral plane, this thickness, okay, this thickness, let us say this is HN. Okay, so this is HN. So if it is HN and this is BN, width at the neutral plane, into VN. So as I'm saying that there is almost insignificant change in the width of that particular sheet. So can I say this and this is going to be almost more or less same? So can I say that VN velocity of the strip at the neutral plane, which is also okay, how can I write it? I can write it HN, no sorry, H1 by HN into VN. This is not something you need to remember. I'm just for the sake of explanation I'm doing it. Okay, this is VN V1. Now again same situation. Since H1 is greater than HN, H1 is greater than HN, then obviously this term is more than 1. Then therefore VN at this particular section, the velocity of the strip VN at neutral plane will be greater than V1. Right. So the same situation you're going to have, since HN is greater than H1, so VN is going to be greater than V1. And this at neutral plane, you also know this neutral velocity of the strip at neutral plane, I can also write this. This is also going to be equal to what? Velocity of the strip at the, velocity of the roller. Tangential velocity of the roller. That is going to be same at any particular point. Tangential velocity hai though. It is simply the tangential velocity at any particular point. So that is going to remain same at any particular point. Right? That is going to remain constant at anywhere on its periphery. So that is not going to change. But at neutral point, the strip velocity of the strip at neutral point becomes equal to the velocity of the tangential velocity of the roller. Okay. So that is how you have to note. So this is a simple understanding that you need to have about this flat rolling process. So you may normally, since in the numericals, most of the time he may be providing the information about this neutral plane or inlet and exit. That is why between any of these three sections you can apply the continuity, or what you can call it as a volume consistency equation, and whatever the required thing over there in the numerical, you can get it done. Okay, so that is the okay. So now let us move on to this further. That is this section that I need to discuss with you is the condition for unaided entry of the strip inside the rules. Condition for unaided entry of the strip inside the rule gap. Okay, what is the meaning of this? See, in this is a basic part that I explained you over here. And if I talk in terms of numericals, from where the numericals will be framed, this is the one area. Rather, there is only a one formula, one or two simple geometrical formulas that we have to utilize. And most of the time, the question is framed only from this section only, right? So if you have little understanding of this section, then your job is done. Okay. Now, what we are going to do over here, I will explain it before I let you know this. What is the meaning of this statement? Condition for unaided entry of the strip inside the rule gap. This is the rolls which are rotating. What you're doing is you are bringing this strip in touch with this particular roller. Okay, let us say maybe by putting this sheet slab through, like moving that chain or kind of conveyor belt, or maybe by pushing it and bringing it to this point, right? So now see, condition for unaided entry. It says that unaided entry means you are not aiding, you are not helping it to go inside. You are not pushing this strip. You are not pushing this strip. No. What it says that if I simply bring this sheet in touch with these rollers, then what is the condition that must be satisfied so that these rollers by themselves pull the sheet inside, right? So when I'm bringing the sheet with these two rollers, so it says that what condition should be satisfied so that without any external aid, without pushing this strip inside these rollers, you simply place it over here and these rollers by themselves pull this sheet inside the roll gap and start deforming it. That condition we want to. Obviously, when we push it, obviously then it will definitely is going to go inside. But let us say if I don't supply any kind of push or force from external force, then what is that condition that must be? So unaided. Unaided means no aid is being provided, no help is being provided to the strip in order to go inside the roll gap. That we call an unaided entry of the strip inside the roll gap. So that condition we want to see. So the same figure has been shown to you over here. Let me first explain you some of the dimensions that have been given to you. Okay, before that, I need to tell you over here, there's a term that is going to be that frequently that is going to be used is draft. Okay. So this was the initial thickness H1, and this is the final thickness that you obtained called as H2. The thickness reduction that took place in one pass. The thickness reduction that took place in one pass. How much thickness reduction took place? You will say thickness reduction that took place is this much, H1 minus H2. So this thickness reduction in one pass is called as a term called as draft. That H, so this is draft. So just keep it in mind, this term that you're going to have is what is the name given to the thickness reduction in one pass that you are going to get. So over here, this is that H we are going to denote. So can I say, if you're denoting it with that H, so can I say this is how much and how much is this? If total total thickness reduction is h1 minus h2 or det h, then obviously this plus this is det h. So can I say this is det h by 2? This is also det h by 2. The half of total thickness reduction, small, right? Same has been shown to you over here. So if you see on one side, I have shown you how much thickness, that is the from here to this distance, from here to here. How much is that? Det h by 2. Clear? And over there, since this is how much is this? From here to here, this is the radius of the roll. This is the radius of the roll. From this point till this point, how much is this? This is radius of the roll. So from here to here, this is the radius of the roll. This is det h by 2. Can I say what is this distance? You will say this is r minus det h by 2. R minus det h by 2. Right? Rest, I have already explained you. Alpha is what? And in addition to it, I'm showing one term over here as LP. So this is the projected length of arc of contact. This. If I project this length, project this curvature, then this straight distance that I'm going to get is LP. It's simply projected length. I hope you may have studied in other subjects also. For example, in case of rivets in machine design also. For example, if this is a circular, if I ask you to drop a light on this particular round cylindrical portion, what will appear to you on the background? You said it is going to be rectangle. So this is the projected area. Right. So what you did, you are having a circular portion. When you projected it, you are going to have the rectangle. Same way, when I am having this arc, if I project it, you are going to have a straight length. I can say this much. And this projected length, I am denoting it with a LP, projected length of arc of contact. That is how I can say. So term you should know, even though I am not going to make use of this particular term over here, but later stage I need this term because I need this in power calculation. LP is the projected. किसको project किया आपने? Projected this arc AB, contact length, projected length of arc of contact. Then the other term I think that I explained you over here, can I write it over here this way? Det H draft, that is det H is going to be H1 minus H2. These are the two terms that we must come to know. Okay, right. Okay, so now let us see then, if we know the basic configuration part, then let us now see what is that condition that must be satisfied in order to, so that these two rollers, one over here, another over here, they by themselves pull this strip inside that roll gap and start deforming this particular strip, start deforming or reducing the thickness of the strip. Now for that, I need to know the force that is being exerted by this roller. So when you will bring this this strip, when you will bring this strip in contact with this particular roller over here, then this roller will try to push this sheet radially outwards. So basically, when you're going to bring it in touch over here, this roller will push it radially outwards. If it will push it radially outwards, that means roller which is rotating is trying to exert a force radially outward on this particular strip. And let us say that force, I am denoting that force radially outward as, let us say, P. Okay. Now, if that be the force at this point that is being exerted, then because at this particular point of contact, then obviously this is also the normal force. If this is the radial force which is getting exerted over here, this force is also normal at this point of contact. Normal mean, as you know, this is tangent over here. So perpendicular to tangent, the force, since the force is acting perpendicular to this tangent at this point, so can I say this is the normal force at this point of contact? And if this is the normal force, then obviously there is going to be friction, because friction depends upon what? normal force and the coefficient of friction, and because these two surfaces are coming in contact over here, basically, so that means definitely there is going to be friction, and that value of the friction is going to be what? Mu into P. And the direction of the frictional force on the strip, right, will be, because this is rotating, so this will try to take the strip along with it. How it is going to take the strip along with it? Because of the frictional force. So it means on this strip at this point, frictional force must be acting in this direction tangentially. So what is the value of that? Mu P. Only then it can take it along with it. That's all. So these are the two forces that you can think of at this point of contact between the roller and the strip. Okay, so I hope you understood. So what I said, since this is rotating, when you will try to bring it over in this point of contact, then you will try to push it away, and push it away, then obviously radial force will be acting. Let that radial force is P, and this radial force is also the normal force at this point of contact, because this is a tangent and this is the normal force. And definitely you're going to have the frictional force, because these are the two surfaces, because they are going to have some kind of coefficient of friction. If I multiply mu into P, then the direction of the frictional force is going to be, because see, this is almost very less speed and this is rotating this way, so this roller is going to exert the frictional force on this direction of the frictional force is on the strip, right? So direction of friction force on the strip is going to be this way, perpendicular to this particular force. That is how you say. And on the roller, obviously, because roller, it will be in opposite direction, it will try to retard the motion of the roller. So I'm not interested in the roller, I'm interested on the strip. So this is how you're going to have. So if I show this force is over here, then I can just, let me show perpendicular to this, that is, you're going to have something this way. So this is the mu P. That's all. So if you have understood these two forces, your job is done. Nothing more than that. There's nothing more than that. Just if you are able to draw it, rest is the geometry part only. So now tell me, what is this angle? What is this angle? This is the same angle, vertical, and this is the same line extending over here. Isn't it the alpha only? Alpha. So this, if this is alpha, this is also alpha. Now tell me, if this is alpha, this and this is perpendicular. This and this is perpendicular because this is tangent. So if this and this is perpendicular, what is this angle? I don't want to make it hodgepodge, but okay, I will remove it. This becomes 90 minus alpha. If this is 90 minus alpha, you're having this horizontal line, you're having this vertical line. Then obviously, what is the remaining angle? This angle is going to be, you will say this remaining angle then going to be what? Alpha only. Okay, so it means I'm removing it, I'm showing this alpha over here only. So that means you're going to have this angle. Where is that? This angle, okay, as alpha only. So what do you do now? Take the component of these two forces, okay, horizontal and vertical component. So if you take the component of this force P horizontally and vertically, same way take the component of this frictional force horizontally and vertically, and then our job will be done. So what I'm doing is I'm taking the same this color. So what is the component downward? It is P cos alpha. What is this component? P sine alpha. Component of this in this direction. And this is going to be P. What is that? P cos alpha. Now let us take the component of what? Take the component of this was this color. Okay. Component of mu P horizontally. What is the component of mu P horizontally? Because this is the angle alpha. So mu P cos of alpha. So can I say over here, you're going to have the component over here. What is that component? You will say mu P cos alpha. Am I correct? And the other component downward is component of mu P vertically downward. What is that component? Can I say this component is what? Mu P sin alpha. So this is mu P sin alpha. That is all. That's all. So now tell me, these two components, because this is a strip, these two components will be forcing the strip downward. They will compressing it. Now, which two components are going to decide whether this strip will go in this direction from left towards right? Because you are bringing this strip in contact over here from this side. So which two components, if these two components are vertically downward, they are going to press it. So which two components are going to decide whether the strip will go from left to right? You will say that only two forces are left. One is mu p, its component in this direction, in a horizontal direction, and its component in a horizontal direction. So since you want to move this strip towards this way, so definitely mu p cos alpha must be greater than p sin alpha. Right? It means for the unaided entry of the strip without any help, if you simply bring this strip in contact over here, and if mu p cos alpha is greater than p sin alpha, then your job is done. Then this rolls can by themselves pull the strip inside. So for unaided entry of the strip inside the rolls, can I say mu p cos alpha should be greater than p sin alpha? P cancels out, and it means mu should be greater than sin by cos. What becomes tangent alpha. So this becomes my understanding. So you should have simple understanding for the what should be the condition that must be satisfied in order for the unaided entry of the strip inside the rules. This becomes my condition. Now the rest part that we are going to discuss is basically the geometry part. Mostly it is going to the geometry part, right? So we will not like go for the derivation kind of thing or something, but definitely we'll see some of the results which are going to be helpful for us. Okay. Okay, one more result that you can have from here as well is in the form of like how do you write the coefficient of friction in terms of angle of friction? So can I write mu is also equal to tangent phi? This is the angle of friction. That is how do you write? You write this. Therefore, if that be the, if I write the coefficient of friction in the terms of angle of friction, then if I input this value over here, then can you say for the unaided entry of the strip inside the rules, phi should be greater than alpha? So if you know this, then obviously that is just the result of this. Okay, that is one thing. Now, this is the only understanding that I have to utilize. We have to utilize. Now, from this geometrical configuration, what I'm going to have is I need to find out the value of alpha, tangent alpha. Okay. What is the value of tangent alpha? So I will not go into deriving that value of tangent alpha, because when we'll write the tangent alpha over here, we will do some kind of approximation, small approximation. Then we will get the value of tangent alpha. So what I will do, I will directly share the value of tangent alpha. So tangent alpha you will get this is one part. Okay, now tangent alpha from the geometry I can get as det h by r. Okay, this formula you need to remember. Reason being that very frequently you have to make use of this formula to find out the value of angle of contact. If you want to find out the value of the angle of contact alpha, which he may ask you or will ask you frequently in the numericals, then you can make use of this formula. Det h you know already now. He must have provided you how much thickness reduction you want to carry out, and then r is obviously going to the radius of these rolls. That's all. So this formula you need to remember. In addition to it, I mentioned over here the projected length of arc of contact. Okay, even though I'm not going to utilize this value in terms of directly over here in this case, but when I will discuss with you this particular force required to deform the material and the power calculation part, there I may have to get this value, and this value turns out to be LP will be equal to R det h. So you can remember this also under root. So if you want to find out the projected length of arc of contact AB, then that can be find out simply by under root of R into det h. Okay. So that's all, nothing else. Now what you do is you will input this value over here. I got this value of, okay, one more thing, you can get the value of alpha from here also, and from geometry also. For example, you could have cos alpha also. I'm just writing that value also. It is up to you, okay, how you want to carry out the calculation part. Just a minute. Okay, for example, if I write down from this triangle O dash R, if I ask you to write down the cos of alpha, will you be able to write? Definitely you will say, what is base? Base is this. This is perpendicular, then becomes perpendicular. This is become hypotenuse. So base by hypotenuse, what is base? Base O dash, this point, R minus that H. R minus that H by 2. This O dash divided by what? Hypotenuse, which is R. So even from here, from this geometry, you can get the value of alpha. So either you get the value of alpha from here, or you get the value of alpha from here. It is up to you. But this formula is pretty simple to remember. So, and regarding the difference between the value that you are going to get from alpha from here and alpha from here will be very slight, very minor. So don't bother about that, because when we calculate tangent alpha over here, we have done slight kind of approximation, right? So there is going to be little difference between alpha value that you're going to have over here and from here, but that value of alpha is going to be very small after decimal point. So you don't need to bother whether you're calculating it from alpha from here or calculating by the simple geometry that you're going to. Basically tangent alpha I got from the geometry only slight kind of that approximation we do. That is the only difference. So it's up to you, just for the sake that okay, you can get it done from here also. That is why I have shared with you. You can just make use of that particular geometry also, but better you just remember this formula. It is going to be helpful. If that is done, then input this value over here. For the what we said, for unadded entry of the strip inside the roll, mu should be greater than tangent alpha, and tangent alpha from the geometry we got this. So therefore what we can do is, if we want to have that case, then in that case what we can do is mu should be what? At the limiting case, this should be greater than or equal to. In equal to, it is not going to pull it inside, but you can say this is the limiting condition or limiting point that you can have. So can I write this way? Tangent alpha become that H by R. That H by R. Now, sometimes he will ask you to find out the minimum value of the coefficient of friction for the unadded entry of the strip inside the rules. Just read my statement again. Sometimes he may ask you to find out the minimum value of the coefficient of friction for the unadded entry of the strip inside the rules. Can you find it out? Obviously you can find it out. What he says, for the unadded entry of the strip inside the roll, mu should be either equal to this at the best case, or it should be greater than that. It means the minimum value of the mu that you should have for the unadded entry of the strip inside the roll should be equal to that H by R, or it should be greater than that. So from this understanding only, simple understanding only, you are going to say that what is the minimum value of mu? Mu minimum should be equal to that H by R under root. That way also you can talk. If we rearrange it, let us say, if we rearrange it, then obviously it is going to mu square. Let us say I make it square. So mu square, R goes to that side. So can I write this way? That H should be less than mu square R. Right? That H remains this side. Mu square, because I have done the square, into R. So mu square R, it becomes that H should be less than equal to mu square R. Indirectly now, he can ask you to satisfy this condition of unadded entry of the strip inside the roll gap. What is the maximum possible thickness reduction that you can obtain in single step or in single pass? for the unaided entry of the strip inside the rolls, what is the maximum possible thickness reduction? This, from this to this. So how much, by what amount you can reduce the thickness from this to this if you don't support it from the outside? That is the meaning of it. So that you can get it from over here. What it says is, to satisfy the condition of unadded entry of the strip inside the rolls, you wrote it this way. I just rearranged it, and now you're having a det h value. That is a draft or thickness reduction. So thickness reduction will be either equal to mu square r, or it will be less than that. Thickness reduction will be either equal to this at the best case, or will be less than that. So if I ask you what is the maximum value of the thickness reduction, you will say maximum value of thickness reduction possible will be equal to mu square r. Otherwise, it will be less than that if you want the unaided entry of the strip inside the rolls. So it means from here the condition came that for the unaided entry of the strip inside the rolls, the maximum thickness reduction, therefore can I say maximum thickness reduction possible when you are having unaided entry of the strip inside the roll will become equal to mu square r. So this becomes your standard formula. Clear? So that is the only one formula that you have to make use of over here in case of this, right? And that covers the whole thing, all the numericals that you are going to have. And almost, if you will see, 95% times he has framed the question from this topic, from this section only, right? And what you need to understand, you need to simply understand what is the meaning of unaided entry of the strip inside the roll. You need to understand the geometry only, and from that geometry you need to know only this much only. Rest part is this formula I just ask you to remember, because it will come from the geometry. You don't need to go for that detail over here. If in any case, let us say if you forgot this formula, then draw this geometry and get it done from over here also. So if you know the understanding, if you are having the understanding of that mu should be greater than tangent alpha, then your job is done. This simply manipulation that you are going, you are inputting the value of tangent alpha. That's all. What else you have done? That's all. Okay. So that is how you have to approach this. That is all in this. So let me just rewind it. What you need to do. What you need to do in this topic. That one is that continuity equation or volume flow rate equation that you have to utilize, because you should have clear understanding that strip velocity will continuously increase and they're going to neutral point, and therefore what you have to do at any section, you can apply the volume flow equation, and therefore you can get the results done. Whatever you simply apply kar sakte ho. And the other one is for unaided entry of the strip, what should be the condition, and just you can practice. Hardly it is going to take 15 minutes for you once you have revised it, right? The whole story, this is hardly of 15 to half an hour, not more than that. Okay, so if that is done, then I think let us first try the numericals from this portion. The other portion that I'm going to discuss will be on the power, and that also we can discuss. Okay, can we now go forward and solve some of the numericals based upon this? Okay, so let me now discuss some numericals with you. Okay, before that, I think I need the help of some more things. Let me just clarify you. Okay, just some terminology part that I need to make you explain. I think it will be better that we solve the numericals. These are some of the terms which will be standard terminology normally used in order to okay. Okay, just see. Draft or absolute draught, I've already discussed with you. Simply the thickness reduction, that H1 minus H2 is the draft. Sometimes you call it as the absolute draught. relative draft or relative draught. That means how much basically is the percentage change in thickness compared to original thickness. This is H1 minus H2 divided by H1. Relative draught, that means percentage or fractional or change in thickness with respect to the original thickness. So relative draught becomes change in thickness divided by original thickness H1. Absolute elongation. Absolute mean actual elongation, how much took place on the sheet. So you're having a sheet of higher thickness, so its thickness got reduced, and where that thickness is going, it is the thickness, that means thickness is getting converted into the length of that particular sheet. So how much, let us say finally initially you are having a sheet of L1 length, and let us say finally it got converted into a sheet of final length L2, then you will say the absolute elongation is going to be change in length. Simply you can say L2 minus L1, meaning is same. Coefficient of elongation, final length divided by initial length. Then you're having absolute spread, like you're having absolute elongation, that actual elongation, absolute elongation and actual elongation that took place, you will say L2 minus L1. Spread, increase in width. As I told you, the increase in width is very small, but sometimes he can provide you the information that this much increase in width took place. So how much width, increase in width that took place, we call it as a absolute spread. Spread of what? Width only. So absolute spread is simply the increase in the width of that particular sheet when you deformed in this particular rolling process. Okay, same way, percentage cold work. Now this term is going to appear very frequently, not only in case of sheet metal forming only, but also in wire drawing, forging, extrusion. In all these cases, this is a general term. When you're carrying out the cold deformation processes, there you can say cold work. So that means percentage cold work. Percentage cold work means percentage change in the cross-sectional area. As simple as that. So in any deformation process, in general way, when you say that percentage change in cross-section area, what is the percentage change in cross-section area? Sometimes we call it as a percentage cold work also, right? Cold work, why cold work? Because if we are talking about the cold working processes only, same way you can talk for the hot working also. If it is hot working, then we'll say percentage hot working, right? Depending upon the process, right? So basically percentage cold work is the percentage change in the cross-sectional area. So if initial cross-sectional area that you are going to have is over here, A1, height, H1, width, this way A1, and finally you are having the cross-sectional area A2. Then what is the change in that cross-section? You will say A1 minus A2 divided by, compare with respect to what? Initial cross-sectional area. So this is simply the A1 minus A2 divided by A1. That is a percentage change in cross-sectional area with respect to the origin cross-sectional area. Now what I have done is I have simply input the value of A1, H1B1, H2B2, H1B1, and since if he has not given any like change in width, then you can say B1 is equal to B2. Then B1 and these values will cancel out. You are going to have the H1 minus H2 divided by H1. So in this case, when B1 is equal to B2, then this value and the relative draught will be the same. Okay. When you're having B1 equal to B2, so these will cancel out, width term will cancel out. So you're going to have H1 minus H2 divided by H1. So we have defined one more term over there, relative draught, right? So they are going to be the same, but okay, just for the relation purpose, otherwise nothing specific in it. Okay, so just have a look. Sometimes what can happen is, sometimes these, even though in most of the numericals that you will see in previous years also, you will not find these terms appearing over here, but sometimes in GATE he can give you a surprise simply asking you, okay, let me know the this coefficient of elongation. Now even though it's pretty simple, but if you have not heard about that term, then you will not be able to calculate this, right? In addition to it, there is one more term that will be used sometimes, and he may ask you to calculate. We call it as a forward slip and backward slip. Okay. Now, from where this term came, first we need to know. See, whenever there is a relative velocity between the two parts which are coming in contact, there is going to be slippage. I don't know whether you have gone through the clutches. So when you are applying the clutch and you are holding it somewhere in between, the two plates of the clutch which are in relative motion, they are going to be slippage. One may be in stationary, other may be rotating. So when the one part is rotating, it is simply rubbing over it. When it is simply rubbing over it, which is basically the slippage which is taking place. And in this process, except the neutral point, where the velocity of the strip and the velocity of the roll are same, there is going to be no slip. Over here. Why? If this hand and this hand, they are in together and moving with the same velocity, will there be any kind of slippage between these two surfaces? No. The slippage will be when this one is moving faster than the other. So if this is moving faster something this way, then obviously there is going to be slippage. So any other point other than the neutral point or neutral plane, you are going to have the slippage. Why? Because there is a difference in the velocity of the strip and the roll. Before the neutral plane, the velocity of strip is less than the roll. So roll is going to slip past the strip, whereas away from the and the points that is towards the right of this particular neutral plane, there the strip velocity is going to be higher than the roll velocity. So in that case, sheet will be slipping past the roll because it has a higher velocity compared to the roll surface velocity. So it means there will be slippage throughout this contact length except the neutral plane. Correct? So that is why two terms have been coined called as forward slip and backward slip. Now, since most of the time we will be dealing with either neutral point, exit, and this inlet, so that is why these slips that we have defined in terms of velocity are either at the exit or at the inlet. So the one slip called as backward slip. So backward slip basically indicates the difference in the velocity of the strip and the roll at the inlet with respect to the roll velocity. Now, reference that has been considered in calculation of the strip is the roll velocity. Why? Because roll velocity is going to remain constant. Strip velocity will continuously change from inlet to outlet, but the roll velocity is not going to change. So that is why if you will see whether it is a forward slip or backward slip, both the difference in the velocity at inlet and exit, they have been defined with respect to the roll velocity, because roll velocity is going to remain constant. Now, see backward slip, you can say this is the maximum slip that can take place at the inlet, and that is how VR minus V1, that is a roll velocity which is constant at any point minus velocity of the strip at the inlet. So this is the difference in the velocity of strip and the roll at the inlet divided by with respect to what? Roll velocity. Same way, the other point that you are going to is at the exit, and exit you are going to have the roll velocity. It's not roll velocity, that is the strip velocity V2. So forward slip has been defined in terms of the difference in the velocity at the exit. So at the exit, velocity of the strip is higher than the roll velocity, and therefore this difference is this divided by the, again with respect to the roll velocity, right? So these two terms you just have to keep it in mind, the forward slip and the backward slip. So basically they are going to denote the kind of slippage that takes place, but they have been presented in terms of the difference in the velocity, and that difference in velocities you are going to get maximum either at the inlet or at the exit. So at the inlet we define that backward slip, at the exit we defined what? Forward slip. That's all. So these are the some of the terms and that we need to remember in order to utilize it in the numericals. So now we are ready with all the things that are required in order to solve any particular numerical. So let's start with the numericals, and here I'm going to discuss with the first one. Okay, just go ahead. All of you should solve all these problems over here only. They are very simple, pretty simple problems. Many of them, some of them I have also taken from GATE also, but they are the straightforward formula based, because nothing special there over in it, or whatever I discussed with you. Only thing is that if you have understood all those things. So can you go ahead with this? So please go see this statement and give me the answer. So using a roll of diameter 800 mm slab of 170 mm thick is cold rolled. Find the maximum possible reduction. Right. So this is how the situation is. So he's saying that, let us say, initial slab of particular thickness is given to me, and that thickness is how much? H1 given to me is 175 mm. Right, this is H1. So 175 mm is given to me, and he's saying that you are reducing it to let us say another thickness H2, and the mu is given to you, right, 0.05. So what is the radius of the rolls? So you just pay attention to this information. Sometimes in haste you can take this information as radius. So that is a silly mistake that is going to be counted. So what is the radius of the rolls? So write it properly. So this is the radius of the roll is going to be 400 mm. So what is the maximum possible thickness reduction over here? So that we have already discussed maximum possible thickness reduction that you can get depends upon the coefficient of friction and R. So it becomes simply mu square into R. So can I write it simply? The maximum thickness reduction will become equal to mu square into R. So simply what is it? 0.05 into R. And what is R? 400 mm. And what is the answer that you're going to have? Any of you who have got the answer, please give it. Let me know what is the answer that you obtained. Otherwise, I need to cross check those values. So I think you are going to get it over what? 1 mm. No, not 1 mm, right? 1 mm, right? So that means 1 mm. So that means in one pass, when you pass it from this side to this side, maximum thickness reduction that you can carry out will be 1 mm. That means what is the final thickness that you are going to obtain? H2. Obviously, initially is 175 mm. Then obviously in one pass, in one go, since you can reduce it by only 1 mm, then obviously you can get it the 174 only. That is the meaning of it, right? So that is how you have to interpret it. Now let's now see the next question. Okay, go for it. Just try to understand this question and try by yourself, right? Just see it. Okay, the thickness of a plate is to be reduced from 50 mm to 25 mm in a number of cold rolling passes. Now see, number of cold rolling passes, it means you cannot reduce this thickness in one go. It is not possible for us to directly reduce it from 50 mm to 25 mm. That is not possible. Number of cold rolling passes, the radius of the rolls is this, and the coefficient of friction is this. So you have been provided the information. So let us say you are having this situation over here. Okay. What is the radius? Radius is given to you already. That is, so let us say initial thickness that I am having is 50 mm, and the final thickness that I want to obtain is 25 mm. So total thickness reduction that I want to give is 25 mm, right? And roll radius he has already given you, that is 350 mm. So just take note of it. And the coefficient of friction is estimated to be mu, has also been provided to you. Determine the minimum number of passes required. Now, since you cannot reduce in one pass, you cannot reduce this in one pass, so you have to carry out the reduction in number of passes. So how many minimum number of steps that you require? The minimum number of steps will depend upon the maximum thickness reduction in each pass. Then only you can get the minimum number of passes. That means in first pass, if I provide the maximum possible thickness reduction, same way in second pass also, if I provide the maximum thickness reduction possible reduction, and third, so in all the passes, if I provide the maximum thickness reduction, from there I can get the minimum number of steps that I have to carry out. So first what you need to do is, yes, you're right. So first you need to calculate the maximum possible reduction in each step or in each pass. So can I say, so maximum thickness reduction, maximum possible maximum thickness reduction possible in each step or pass. So what is going to be that? You will say in each pass the maximum possible reduction that you can obtain is mu square into r. So what is that? So you're going to have 0.15 square into r is 350. So how much is that? Can anybody let me know how much is that value? So maximum thickness reduction possible in each step is how much? I think can anybody help me out in this? Okay. Just a minute, okay? Let me just see. So yes, 7 point, I think that is a 7.875, 7.875 mm. So that means in each pass you can reduce the thickness maximum by 7.875 mm, right? So in how many passes you can reduce the thickness from 50 mm to 25 mm? So if you say that if n are the number of passes that you need to take, and in each pass if you are reducing by 7.875, then that reduction must become equal to 25, 50 minus 25, or simply number of passes will be equal to the maximum thickness, sorry, total thickness reduction that you have to carry out, that is 50 minus 25, 25 divided by what? The maximum thickness reduction that you are carrying out in each pass, that is going to give you the number of passes. So this number of passes become equal to what? So if you divide it by this 25 by this, I think the whatever value that you have calculated is 3.17. Now pass cannot be in fraction, either 1, because if this is a whole coil, then either 1, 2, 3. So basically it is going to be the whole number only. It cannot be in fraction. So that means, what is the meaning of this? The meaning of 3.17 is that when you take the maximum thickness reduction in each pass, then in three passes you have to give this maximum thickness reduction possible. But in the fourth pass, whatever is the left out, that amount of reduction you have to carry out. That means fourth pass you don't need to go out for the maximum thickness reduction possible, because if you go for the fourth pass also, if you go for 7.875, then that final thickness will go below 25 mm, right? So in 3 passes, whatever the thickness reduction that you have obtained, in the final pass you have to take the thickness reduction lesser than that, which finally reduces it to 25 mm. That is the meaning of this. So it means in any case you have to make out the 4 passes, but only difference being in first 3 passes maximum thickness reduction you have to carry out, in the last pass you have to carry out whatever is the left out in order to achieve the 25 mm. Okay, so same way, okay, this is the first part. Determine the minimum number of passes required. Minimum number of passes required is 4. Second part is, this is the first part. What does the second part says? Second part says that if you take equal thickness reduction, if you take equal thickness reduction in all the passes, then in each pass how much thickness reduction you have to carry out. You already know In any case, you have to give the 4 passes, and that too 4 passes are the minimum passes that is required. In any case, you cannot complete the job without 4 passes, right? So, but if in each pass I want to give the equal thickness reduction, over here you are not providing equal thickness reduction in all the passes. You are providing equal thickness reduction equal to maximum possible in 3 first passes. In the final passes, you are providing lesser one. But if you want to have the maximum, equal thickness reduction in all the passes, then that is going to be equal to what? So what is the draft in each pass? Draft in each pass when equal thickness reduction is carried out. Equal thickness reduction is carried out. So what should be that? It should be simply how much thickness reduction you have to carry out? 50 minus 25. In any case, you have to reduce this thickness by 25 mm. And if you want equal passes, then you need to, how many passes? 4 passes. So if you need 4 passes, then simply what do you do? 25 divided by 4. That means I think it turns out to be 6.25 mm. So that means if you will give 6.525 mm, and now see the difference. This is the maximum possible. This is not the maximum possible. So this is in each pass you can have, in all the 4 passes, give the thickness reduction of 6.25. That is also possible, right? So that is the meaning of this. Okay, so I hope you understood how to find it out. Let's move on to the next one. Yes, right. Okay, so let's move on to the next one. Okay, go ahead with this and be fast. Pretty simple, nothing special in it. Now see, you're having only one formula, okay, that will be manipulated again and again. So if you have the clear understanding, nothing, you don't need to worry. So go ahead, just see the question and give me the solution and be fast. Within 1 minute, you should be able to solve this particular question. 40 mm flat plate is to be reduced to 30 mm in single pass cold rolling operation. 40 mm flat plate, reduce thickness reduction in single pass. So you want to reduce it in one go. So that means, can I say thickness reduction possible? No, not possible. That you are going to provide is how much? 40 minus H1 minus H2. So this is the draft that is mentioned that you need to obtain, that is 40 minus 30 mm. How much is that? So you want to provide a 10 mm thickness reduction in a single step. Okay. Determine the minimum required coefficient of friction if roll diameter is this. Again, take note of this is diameter. So I need in my formula the radius. So it is not the 600, but this is 300 mm. Now, what is the minimum coefficient of friction required? That is, he's asking for minimum coefficient of friction required in order to carry out this process. Now, even though he is not mentioning anywhere for the unadded entry of the strip inside the rolls, but whatever all that you have discussed based upon that only. So it is understood that you have to go for the based upon the unadded entry of the strip inside the rules. Okay, so go ahead. What to do? So as simple as that, I have told you what is the required condition. You are having mu should be greater than equal to, immediately you must be able to tell, and that h mu should be greater than equal to that h by r. That's all. That's what is the formula. As simple as that. So that means minimum, when at the minimum it should be, that means the least value of mu can have is equal to this, or it can be greater than that. If you want to unadded entry of the strip inside the roll, it should have minimum value equal to this, or should be more than that. So what is the minimum value? Becomes equal to this. So mu minimum you will be able to get from the mu is equal to mu minimum is equal to det h by r. So Just input the value. How much is that? That h you want to obtain is 10 mm. Our radius is 300 mm. So how much is that value under root? So what is the value that you got? 0.18. All of you are getting. So I will go with your value only. 0.18 is going to be the answer. Okay, so 0.183. So B stick to, I think, okay, anyway, 0.18 or 0.183. It is okay. Let's go to the next one now. Sorry. Okay, go ahead with this and be fast. I think this is gate question, 2004 question. Okay, and try to calculate it within 1.5 minutes or so, right? In a rolling process, the sheet of thickness this reduced to this, rolls are of diameter 600 mm, rotates at this, roll strip contact length will be. Now, first thing is that you need to interpret the meaning of roll strip contact length. I hope you must have interpreted it correctly. What is the roll strip contact length? Roll strip contact length is the portion or the length of the strip which is in contact with that particular roll. That is a roll strip contact length, isn't it? So if I ask you, this is the center. So if this is this, so this is alpha. And what is this? This is R. So what is this roll strip contact length? Roll strip contact length AB. He is asking. What is that? AB. He's asking. So can I calculate? This is R into alpha. And if I writing it alpha over here, this should be in radians, right? So roll strip contact length becomes simply R into alpha. So alpha, how can I find out the alpha? You are having the formula. Tangent alpha is equal to det h by R. That is one formula only. Just get the value from here. So from here, you will be able to get that tangent alpha is equal to what? Det h is how much? How much is the thickness reduction? 25 minus 20, 5 mm. And what is the radius of the roll? 300 mm. That's all. Under root. From here, you can get the value of what? Alpha. And this value of alpha that you're going to get over here, I think this is going to be in degrees. Okay. So what you need to do is you need to convert this value into radians. So this value is going to be 10 alpha is 3.57 degree. 3.57 degree. So check it out. So, and you need to convert, because over here when I want to find out the roll strip contact length, then you need to input the value of alpha in radian. So I need to convert this value into radian. So radian, it turns out to be 0.0622 radians. Okay. So if that be the case, then input the value. So roll strip contact length AB become equal to, what is the radius of the roll? 300 mm. 300 mm, and obviously this value is in radians, 0.0622. So this turns out to be how much? This turns out to be, oh sorry, I have done some mistake. I am taking the reference somewhere. So have you calculated it? Have you calculated it? I don't know which one is that. I need to see how much that calculated value. Fourth is how much? Fourth, you're going to have, I think this value turns out to be 7.35. 7.35. 7.35. 7.35, and oh sorry, this becomes degree, and it turns out to how much? So this is 0.128. 0.128. 0.128 radians. So just what you do is 0.128, this become radians, and then this value will be how much? So you're writing it 39 mm. So hopefully it should be same. So how much is that? 38.4 exact. Okay, as per the answer, 38.4 mm. So it means you're going to have the correct option as B. Okay. So can we move ahead now? Okay, let's move on to the next question now. Okay, just a minute. Okay. So go through this particular question now. Okay, just go through it. A strip with the this cross section, this is being rolled with 20% reduction of area using 450 mm diameter rolls. Angle subtended by the deformation zone. What is this deformation zone? Basically, it's a roll strip contact length area, right? At the roll center in radians. So what is given? What he wants you to find it out over here? He wants you to find out the alpha, and that too in radians. What is the value of alpha in radians, right? And he has given you all the information for that. So what is the thickness of the strip? Over here, this is the cross section he has given. Then obviously the initial thickness that you're going to have is equal to 4.5 mm. And it is being rolled with 20% reduction of area. What is the meaning of 20% reduction of area? It means percentage reduction in the cross-sectional area. He has provided you. So can I write it this way? Percentage reduction in cross-sectional area is what? A1 minus A2 divided by A1. Change in cross-sectional area with respect to the original cross-sectional area that he has given you is 0.2. That is 20% in fractional form. Can I write this way? And if you input the value of A1, H1, B1, H1, H2, B2, then obviously since he is not mentioning anywhere about the increase in the width, then obviously for me width is going to be constant. So can I say this way that H1 B1 minus H2 B2 divided by what? H1 B1. So over here you're going to have H1 minus H2 divided by what? H1. Right. So since you have the H1, you can get the value of H2 also, or that H also directly you can get it over from there. It's up to you. So that is how the information is given. Now to find out the alpha, what do you need? You need tangent alpha only. So tangent alpha is how much? Dat H by R only. So can I write it this way? Tangent alpha is equal to how much is dat H? Dat H can I find it directly from over here? I obviously H1 minus H2 is what? Dat H only. Or if you want to find out H2, you can find it out H2 also. So can I write it dat H as what? 0.2 into H1. So 0.2 into H1 is 4.5 divided by what? This becomes dat H divided by R. What is the R? Radius of the 450 divided by 2. 450 divided by 2 under root. From here, I'm going to get the value of alpha. So alpha turns out to be what? I don't know how much. Has anybody calculated? 0.06 radians. I don't know. I need to check it. So maybe it must have been done somewhere there. So it turns out to be, or how much is 3.61? 3.618, 3.618, 3.618 degree. And in terms of radians, I think you have given me the value 0.06, 0.06 radians. That's all. So sometimes he will ask you to calculate alpha, sometimes R, sometimes dat H, H1, H2. That is how the simple manipulation is going to be. As in general, if you ask me, there is only one formula in the rolling of the strips, right? And that simple understanding if you have, then you can attempt any particular question from this particular section. Okay, so let's go to this particular section, this now. Okay, just see this particular question and attempt it. and be little fast, okay, so that we can move ahead to next section. Okay, I need to discuss with you one more kind of problem that is normally appears over there. So okay, this is what you're having. Okay, go ahead. Okay, so what is given to you? A plate having 23 mm thickness is rolled to this. If it is the maximum, so he's saying this is the maximum thickness reduction possible. Okay, determine the coefficient of friction. Pretty simple. Roll diameter given to you. What will be the values of the backward? Don't commit the, again, I'm stressing, most of you commit the very silly mistakes in the exam. Even though there are so many, we are telling you that there are so many simple questions which are framed in the exam, but most of you commit the silly mistake in the simpler questions. And that is where basically the score goes down. So in haste, sometimes you have read it as a diameter as 450 mm while you started calculating. In calculation, you are taking it as a radius. So that is how you commit the mistakes. Okay. So please, whenever you are having such kind of information, immediately note it down so that the error goes down. When you will write radius, then immediately it will type, okay, it is the diameter. So you will write it this way. So your job is done. So the possibility of committing the error will drastically go down. What will be the values of backward and forward slips if the plane thickness at the neutral plane is this? Now, here he is asking to calculate the this H1. Go ahead and calculate by yourself, and then you can see the explanation part also. H2 he has given you 18 mm, and if he's saying there is a maximum reduction possible, then what is the value of this? And the radius of the roll is equal to 450 by 2 mm, right? And if we say this is the maximum thickness reduction possible, so you know H max is equal to mu square R. Then from here you can get the value of mu. So can I write it this way? What is the maximum reduction possible? This is 5 mm is equal to mu. He has not given you, but R you definitely know, 450 by 2. So from here you can get the value of mu. And what is the value of mu? So anybody please help me to get this value. And I think it is going to be come out as a 0.149. All right, okay. 0.149. This is the mu. This is the first part that you have done. Now go to the second part that he is asking you to calculate. What he is saying that obviously you are going to have this kind of situation where he has provided you the detail in the neutral point. Something this way. And over here, this is how you're going to have. So somewhere here, you're going to have this one. So he has even given you the thickness at this. So obviously initial and final thickness, you know. And at the neutral plane, also you know the thickness. Right. At the same time, you have one more information, you know, at the neutral point, you're going to have the velocity of the roll. Right. Velocity of the strip is neutral point. We are going to denote it with Vn. Velocity of the strip at neutral point is going to be the equal to the velocity of the rolls. So it is going to be the velocity of the rolls. So this point you have to keep it in mind. Now, what he's asking you to calculate? He's asking what will be the values of the backward and forward slips. Now tell me, what is the backward slip? Backward slip. So you know already, backward slip is simply what? At the inlet end. The difference in the velocity of the roll and that of the strip at the inlet. So with respect to what? Roll. And you know, over here, the roll velocity is definitely going to be greater than initial velocity of the strip. That is how the situation is. This is V1 and this is V2. So can I write it this way also? 1 minus V1 by R. Now, VR, that means velocity of the roll at the neutral plane. So over here, I need to take help of what he has given you. He has even given you the thickness at the neutral plane. So I need to take the help of the velocity consistency. Okay. volume flow rate consistency over here. So what you can do is, since this particular information that you are having is between what inlet plane and the neutral plane, you can apply the volume consistency equation, volume flow rate consistency equation between the inlet and the neutral plane. So how can you write that? So can I write this way? So V1 A1 V1 is equal to what at the neutral plane? AN HN H1 B1 V1 equal to H2 B2. Sorry, this is at the neutral plane. HN BN VN. So since no information has been provided to you, forward slip, I think you are saying 0.264. I don't know, forward slip, forward 0.264. No, forward slip you are calculating wrong. I think it should be near this value that you are giving is near for the backward slip. I think that is near to that. Okay, this goes out because you have not been provided information for the width. So what I need, V1 by VR. Vn is equal to what? I have written it over here. So Vn is equal to velocity of the strip at the neutral plane is equal to velocity of the roll. So can I write it in terms of V1 by VR? Obviously I can write it. So just write it down this way. So can I say that Vn or VR, sorry, V1, I need V1 by Vn. V1 by Vn is equal to Hn by H1. Yes, that's all. So if that be the case, just input this information over here. 1 minus V1 by Vn is what? Vn is equal to Vr. So V1 by Vr become equal to Hn by H1. What is the Hn? So Hn you have been given over here as somewhere 18.3, 18.2. If the plate thickness at the neutral plane is 18.2, so can I say Hn that you are going to have over here is what? 18.2. So 1 is what? Sorry, 18.2 divided by what? H1 is what? 23. See this value. This value should be backward slip value that you are going to get is 1 minus 18.2 divided by 23 becomes equal to 20.86%. 20.86%. It is going to be 0.2086. Yes. So that is no. I think you are writing it otherwise. Backward slip you are going to have this value. Okay. What about the forward slip? You can go ahead and calculate the forward slip also. So forward slip is going to be on the similar line. Forward slip. So how can you write the forward slip? You can write this way. Right? How? So that means again, difference in the velocity at the exit, and at the exit with difference velocity, roll velocity, strip velocity will be more than roll velocity divided by with respect to roll velocity. So you're going to have V2 by, can I write VR as Vn? Obviously I can write it. Why? Because at neutral point, roll velocity is equal to the strip velocity. Again apply the, now in this case you can apply this information between the exit and the, because you are having this information neutral plane and the exit. So can I say H2 B2 V2 is equal to Hn Bn Vn. So it goes and you're left out with what? V2. Sorry, this is I need V2 by Vn. So V2 by Vn, which is equal to R V2 by Vn, Hn by H2. Okay, so can I say this way? So this is Hn by H2 minus 1. So how much is Hn? Hn again you are having 18.3. 18.2 divided by H2. H2 is how much? H2 you are having 18 minus 1. So this value turns out to be how much? 1.11%. 1.11%. Okay. So that is how you have to attempt it. Okay, so 1.1, right, okay, 1.11%. Okay, okay. So let me now discuss with you one more kind of this area from where the question is framed. Okay, and that area is related to your calculation of power. Okay, so this is the area from where sometimes he can frame the question, and this is related to the amount of force required to deform the material. Okay, and first series, elementary assessment of the rolling load and power. What is the meaning of elementary assessment? Yes, today we will do rolling only, right? So elementary assessment of load or power. Elementary assessment mean very basic. We are not involving the advanced analysis in analyzing this power and this calculation. That is why elementary. Assessment, you want to estimate. You cannot tell the exact value. That is why you want to estimate. So elementary basic estimation of the rolling load in this particular rolling process. Now see, this is how exactly the rollers are, and when you deform them, you know you are having a curvature surface. That is how the deformation, actual deformation takes place. But what we assume while estimating the load required to deform this material is that instead of the rollers, this strip is being deformed by simply a platen. Platen is simply a kind of, you can say, what should I say? Just a minute, okay? Kind of this surface. You can say this one, okay? This is a flat surface. Instead of being pressed by the roller, we are assuming that it is being pressed by a platen. We can call this as a platen. Why we can assume so? Because particularly in case of cold rolling, this contact length is basically relatively small, and this thickness reduction is not that large. Over here, we have shown it too large, but in practice, this is very small. So it will look as if this is straight only. Even though this is a curvature, but this curvature is very small. Just have a look over it. Very small curvature over it. Had I deformed it from here, then it would look like, okay, there is a large curvature. So in that case, if I will carry out that assumption, then it will be not give that good result. So that is why, since in actual rolling, particularly in cold rolling, you are having a very small amount of deformation. So we can approximate this curve with the help of a straight line. Okay. So that is why if you see, even if actually I am deforming with the help of the roller, I assume that this is being deformed with the help of the platens, right? Having a what? Having a length equal to the projected length of arc of contact. Now here comes the point that is we were talking about. Actual length of arc of contact is what? Actual length of arc of contact is AB, but projected length of arc of contact is what? If I simply project it, so I am going to get the straight distance. So if I take that particular platen of this particular length called as projected length of arc of contact, and obviously it is going to have the width equal to the width of the strip, and then simply press it from top as well as from the bottom, then we can very simply estimate the force required to deform the material. And in that case, if I say, if I'm deforming something with the help of a straight surface, flat surface, then can I, if I know the stress value, will I be able to tell you how much force is required to deform this material? You will say, let us say if I apply the force F over a same situation you're going to have over here also, okay? So let us say that force required to deform the material, how do you write that? You say stress into area. This is how you write stress into area which is getting deformed. So the stress that we are going to deform over here is, we are going to write it over here as true value of the flow stress, right? And if I multiply by area, and what is the area which is getting deformed? You will say this is the projected length of arc of contact, and obviously is going to have the width also, which is not visible over here perpendicular to this board. So width is B that we have denoted, and this is a LP, projected length of arc of contact. So can I say the projected area? Oh, what is that? B, width of the sheet into projected length of arc of contact. That's all. And you know, in this case, if I multiply it with this, what is, have I calculated the value of projected length of arc of contact? I have already calculated. What was that value? R into that H. That is why I just gave you that particular geometric formula over there, that I needed it over here, right? So this becomes the force required to deform or press this particular sheet in order to reduce its thickness. Okay, now just have a look over here. I will not explain it in detail over here, because the same term I am going to explain you over there in case of wire drawing also. Stress, I have written something different which you are not aware of. I have not written something this way. Neither I have written the true stress, but I have written is the average value of true stress. Okay, so basically in plastic deformation processes, we will see in case of for all the plastic deformation processes, whether you talk about rolling, forging, extrusion, or wire drawing, since the material is being deformed in the plastic region, we have to make use of the stress strain, or true stress, true strain concepts. And as you know, as the material is being gradually deformed from this point to this end, so the strength of the material is gradually increasing. Okay, so since the strength of the material is increasing, so if I want to have a simple formula, it becomes difficult for me to analyze it. So that is why what we do is we take the average value of the true stress. This average value of the true stress, we call it as a flow stress, because basically the flow term came from that, because material is flowing in the plastic range. In actually, we have to provide more power, since it is not just compressing but also drawing or pulling it. That is why I said, see Nitesh, what I said is, this is simply the estimation. We are exact value. Definitely there is going to be difference. Lot of difference is going to be over there. But initially, it is not that we are having only this formula in order to calculate the power or in order to calculate the force required to deform the material. We can, if you take this curvature portion, then we can integrate also. We can carry out the integration and find out the exact value also. But at the basic level, we try to simply estimate. We don't try to be exactly, we don't try to be exact. We try to estimate, want to bring it close to it, so that it becomes simple for us to analyze the things, right? So there is going to be difference over there in these values, because there is going to be approximation. Okay, so what I said is, in this case, we are not taking simply the convention stress. Convention stress we don't discuss in case of the plastic deformation processes. We talk about the true stress also, and that in this situation, since the value of the stress is changing from inlet to exit, so we are going to take the average value of the true stress, and this average value of the true, that is what we are saying, bar of what true stress. So this value we called as the flow stress also. Flow stress, the meaning of flow stress is that the material is flowing in the plastic range. Plastic, when you are plastically deformed, material is flowing. The stress, instantaneous stress existing in the plastic range, we call it as a flow stress, right? So this term, even though over here I don't want to discuss with you in detail, little bit clarification more I am going to give you in case of wire drawing. So just take note of this, that this value that you are going to have, you are going to use over here for the stress will be the mean flow stress. Mean mean average, mean or average flow stress, or alternately you can say average true stress. The meaning that you are going to have will be same. And LP I have already discussed with the projected length of arc of contact. Okay, that's all. Nothing we have to do over here. So let me just sum it up. What I did, I simply assumed the rolls as a flatten, because contact area, the amount of deformation is very small, so it looks like as if straight. So if I simply press it, then it will get highly simplified. So if you simply press it, then if I want to find out the stress, how do you find out? Force that you are applying divided by area. What is the area that is getting pressed? You will say area is this into width. So what I did is stress into area. So area I already know, LP projectile length of arc of contact into B projectile length of arc of in terms of geometric configuration I'm having this value, and over here stress, we don't talk about the convention stress over here, we talk about the flow stress, average stress, or sorry, true stress, and that too over here the situation is something like the value of the true stress will be changing, and therefore we are taking the average value of the true stress. So is going to provide you these values, that's all. So this becomes the force required to deform this material. Elementary assessment of the rolling load, or force required to, or the rolling load required to deform this material. Nitesh, either like already I think whole of that particular videos are already there on YouTube. I have already made on this true stress strain. Just go watch all those videos. I think the whole thing will become clear to you. How to calculate flow stress and all that, mean value of flow stress and all that. So I don't need to discuss it over here. So already they are on the YouTube over there. So just go and watch those videos. I think that thing will be clear. But as of now, I think that will be more than sufficient. Okay, so in addition to it, one more thing that I need to discuss with you is the power calculation. Okay, so now it's the same configuration that is shown to you over here. Same thing I am just showing you over here. Only difference being, just a minute, okay. No, this was that. Okay, let's talk about the power that we are going to calculate. Okay, again over here also we are going to estimate the power. So now just have a look over here. What I have done is we will extend the same analogy. Let's say if I ask you, if I am pressing with the force PF over here, if I am pressing this particular material with force F, what is the reaction that rolls are going to have? You will say the same amount of reaction that is you are going to obtain for the same amount of reaction that you are going to get for the rollers also, or the platens also. Can I say if I am applying force F on the strip downward this way, then obviously same amount of reaction that you are going to have in the opposite direction on the rolls. Okay, so same thing has been shown to you in terms of reaction over here. It's the same diagram. Only thing is that the force that I'm exerting on the strip as a reaction force on the rolls is F, right? So that is why sometimes the same force, keep it in mind, this is not the only force required. Okay, let me just give the description, complete description. Sometimes you can write it as this way also. Force required to deform the material. Or sometimes you also call this force as a roll separating force. Roll separating force. That means I'm applying the force F to deform the material, but the same amount of force is trying to separate these rolls because it is acting as a reaction force on the rolls. So either you call it as a force required to deform the material, or you call it as a this is the same force which is also separating these rolls. So just don't get confused if we ask you to calculate roll separating force. So it is the same force which we know it as a force required to deform the material. Okay. Now same force has been shown to you over there this way. This F, I think it is visible. F has been shown to you over here, and this F I have shown you acting at the middle. For the sake of simplicity, we have taken, even though this force will be entirely distributed on this arc of contact, but we are assuming that it is acting from the center. Now I want to calculate the power required to deform this particular material. And how do you calculate the power? Power you rewrite by a very basic equation, 2 pi n RPM of this particular rollers into torque divided by 60. This is a general equation that you know. So if I want to find out the torque required or the movement required to rotate the rolls, so how do I need to calculate that? So I need two things over here. So again, this is again the simple understanding that you have to utilize. if I want to rotate this roller in this direction, let us say, so this roller need to overcome the movement which is being supplied by this roll separating force. Now this force is acting this way. Now tell me, where is the center? Center is over here. Now this is the center, and let us say lambda is the distance between the center and the application of the force. Now see, this is the center, and this force is acting upward. This force is going to create a movement in clockwise direction. And what is the magnitude of that movement? The magnitude of this movement is, okay, I will take another color. The magnitude of this movement about the center is how much? You will say force which is acting and the perpendicular distance which is lambda. So can I say the movement that is acting about the center of this roll is F into lambda, isn't it? And until and unless this roller overcomes this particular movement which is acting in opposite, I want to rotate this roller in this direction, but there is a movement which is going to act in the opposite direction. So until and unless I overcome that movement, this roll cannot rotate. So it means the torque that I need to supply over here must be equal to force which is acting, roll separating force multiplied by the lambda. This is the distance. Okay, and this distance, same situation you are going to have over here also. This distance is lambda, and since this is acting downward, now see the direction. I want to rotate this roller in this direction. I want to rotate this roller in this direction, but this movement created by the deforming force is acting in the opposite direction. So until and unless I overcome this this movement due to this force F, I cannot rotate in this particular roller. So what you need to do in this case is that simply take the movement which is F, which comes from this particular roll separating force which was acting over here, and the distance which is lambda. So sometimes we call this lambda as a lever arm, where lambda is called as lever arm. Lever arm, simply the distance, sometimes you can say eccentricity also, whatever name you want to give, where the force is acting. Now for basically this value is going to be different for cold rolling and hot rolling, but this must be provided to you because these are the approximate values. These are not the exact values. So I'm just sharing with you the values, but only that values should be taken as a reference. Okay, so this value, I think, just a minute. Okay, so here that value is over here. So this lever arm value is LP by 2 for hot rolling and 0.45 for cold rolling. Okay, hot rolling के लिए 50. Okay. Or simply you can write 0.5. Okay, just a minute. Okay, I will write it this way. Either you can say 0.5 for hot rolling and 0.5. Okay, 0.5 of LP by 2. Okay, that's okay. And 0.45 of LP for cold rolling. These are just the reference value. So he must provide you the value of the lever arm in order to estimate the value of this torque. Okay, otherwise in general I don't think that you have to make use of these values anywhere. This is just a reference value, but you must know the distance where this force F is assumed to be acting. As simple as that. Okay, so from here you will be able to get the movement. Just input this movement over here and you're going to get the power. Now this resistance that you are talking about, this movement that you were talking about, or the power that you need to supply, this is for one roll only. Okay, so because you're going to have a motor over here, you're going to have another motor over here. So this power required in order to deform this particular material through this particular roll will be this much. But since you cannot carry out operation with the single rolls, you need two rolls. So that is why you need two. If we want to calculate the total power in the operation, that you have to multiply it by 2. So this more specifically power that I calculated is per roll only. Okay. So power required in order to deform the material per roll, let's say this will be this much. If you want to calculate, if he is asking you to calculate power required in the rolling operation, then in that case you need to consider the power required from this particular roller and the power required at this particular roller. In order to deform the material, you have to multiply by it 2 to get the total power in the rolling operation. Okay, so that is all that you have to know. So what we did is, let me sum it up. You are having this particular force required to deform the material. That force in itself is also the roll separating force, and from that roll separating force we assumed it acting somewhere in the middle, and then by making use of the concept of the movement, we calculated the torque in the power equation. And since this value is for this one roll only, so this becomes the power per roll. If you want to calculate for the two, you can get it done. Okay, so that is a simple concept that you have to utilize. So let me just discuss one numerical with you before we wrap it up. Okay, so just go ahead and it'll be a little fast. Just see this question. In a single pass rolling operation, 20 mm thick plate okay, of which this is reduced to 18 mm, right? The roller radius is given to you, rotational speed is given to you, and average flow stress. Directly he has mentioned you the average flow stress or mean flow stress of the plate material is this much. The power required for the rolling operation in kilowatt is what? Now keep it in mind, he's asking you to power required for the rolling operation. So it means power required, total power required will be what? Total power required will be what? Will be 2 pi n into, sorry, 2 multiplied by what? 2 pi n into mt divided by 60. As simple as that. So this is the power required for the single roller, and since there are going to be two rollers who complete the process, so definitely you have to multiply by this. Now for mt, first you need to calculate, and mt is going to be come from where? The force required to deform the material multiplied by what? The how much? Since he has not given anything, if he has not mentioned about anything about the torque arm, then what we will assume? We will assume that this force is exactly acting at the center. Or okay, got the point? So this from here to here, what is this? This is the projected length of arc of contact. Projected length of arc of contact is this. So if he has not given any kind of this data, then simply you will assume that this force will be acting at the exactly at the middle of projectile length of arc of contact. So this becomes equal to lambda becomes equal to what? LP by 2. As simple as that. So in that case, what you can do is F into what? LP by lambda is what? F into LP by 2. Okay. Now rest, you know, F you can get it done from where you need to calculate force required to deform the material. Kahan se aayegi? It is going to come mean value of force stress multiplied by what? B into projected area of length of projected length of arc of contact, and which can be provided given by what? R into that H. So has he given you the values? Definitely he has given you all the values. He has given you this. Can I write it this way? 300 multiplied by what is the B? Width is he has given you 100. What is R? R he has given you how much? 250 by 125. Sorry, he has given you 250 only. So this becomes Newton per mm square. If this is Newton per mm square, these values should come out in mm square only. Okay, mm over here, mm over here. That H, how much thickness reduction is taking place? A 20 mm thick plate with the which is reduced to 18. So 2 mm thickness reduction. So can you get me the value of F? So F that you are going to get over here, I think it is going to be 670.8 kilonewton. Okay, done. If F you know, then just simply input the values over here and you're going to get MT, you know. So just input this value. Can I write it this way over here? So 2 into 2 pi n. How much is n? N is 100. Sorry, 10 RPM. 10 divided by what? 60. 60 becomes what? Revolutions per minute. So I am converting minute into second by dividing 60. Now this value torque should be in Newton meter. Oh, sorry, in Newton meter. So that means multiplied by what? Now you are having force. Force is how much? 670.8 into 10 raised to power 3. This becomes your force and LP by 2. So what is LP? LP again R detached by 2. Okay. So I have not calculated this value, but okay, you can say into R. R is what? 250 into 2. R detached by 2. LP. I'm just directly inputting this value over here, empty. F, I have inputted this value over here. LP, I have taken as what? R detached. So R detached becomes what? 250. So 2 should be separate, I think. It should not be this way. It should be this way. 250 into 2. This become R into detached. That means LP divided by 2. Okay, this should be this way. Now, but keep note of this is in Newton. This value I should take in meter. So if you have to convert it into meter, I am multiplying it by 10 minus 3. Okay, this was in mm. So I have converted this value of mm into meter. Now get me the value of total value that you are going to have. So this value that you are going to have will be equal to, I think, what? 15.69. 15.69 kilowatt. Right? So just pay attention to the units. The rest, I think it is pretty simple. So more or less from this section, if any particular question is framed, that is only for the calculation of power only, and the straightforward formula that you are going to have, simple formula that you are going to have for the power over here. So just utilize that formula and get the things done. For force, you are having direct formula. For the power, you are having this simple formula that you can utilize. So I think that is all in this particular topic that you are having. And what I think is, if you have gone through all these questions, I have almost taken like maximum variety of questions that can be framed from this particular topic. And even if you want to see some more questions, then you can just try the previous questions from this particular section. So I think that will be more than sufficient for you from this particular section. So that is all from my side. And see you in the next topic. That is going to be, I think, tomorrow at the same time. That is your drawing. That is a wire drawing section. So till then, bye. Thank you.